So in the last lecture what we went through was a review of a metric SI and the concept of system, surrounding, boundary. Now we are going to talk about intensive and extensive properties. Okay, so let's look at a thermodynamic system which may consist of many species. For example, you can look at nitrogen, hydrogen and NH3 in a similar example which we had earlier in the lecture for the production of ammonia. Now if you want to understand change of the state of the gas mixture, if you change the condition, then you need to know the property of the materials. The property of the materials in this case, which depends on temperature and pressure, you have to choose a specific set of properties such as odorless or other properties which are relevant for potable water, for example, is not relevant for thermodynamics. In thermodynamics, the properties which are related to energy and its transformation are only useful in the analysis. So the essential features of a property would be that it should have a definite value when the system is in a particular state. Again, as I said, properties such as odorless or tasteless are not useful in the thermodynamic analysis. You have to choose properties which has a certain value which is related to the energy or change in energy. So a property should have a definite value when a system reaches a specific state, and the value of the property should be determined irrespective of how that particular state was achieved or was brought to that particular state. So it doesn't matter how the state was achieved, the property should depend on the final value. So the change in the property from one state to another state can be clearly written in this expression, where Z is a specific property and a change in the Z value from some initial state to the final state is given by the difference between these two difference between the value of the Z in two particular state. Now let's little bit look at the mathematics. So if you say Z depends on two variables x and y, you can write the differential of Z in the following form, where the partial differential of Z with respect to x is given by m, and this is n, and mathematics tells us that if this condition holds, then the dz is said to be exact differential. Now in such condition you can integrate this in this form. That means you can write del z as an integral of dz from I to f, and this would be given as the difference between z of final and the initial values. And therefore thermodynamics property z is an independent of the path because of being exact differential and is a point function. So this is a definition of the point function.
Okay, so let us look at common properties of a system. The examples are pressure, temperature, volume and mass. The properties can be extensive or intensive. So just take an example. Let us consider a system. This system can be simply water or any fluid, okay, having a mass m, volume v, temperature T, pressure P and density rho. Now you divide this particular system into two parts, okay, and that you can do in this form, where you have divided into part 1 and part 2. Now the mass certainly gets divided by 2, volume certainly gets also divided by 2. On the other hand, temperature of both the parts should remain same, the pressure should remain same, and as well as the density. That is what we can understand from our daily experience by taking water in a glass and dividing into two parts. So certainly certain properties are affected by this aspect of let us say division of the volume, which means it depends on the volume or the mass. On the other hand, the other properties do not, such as temperature, pressure and density. So that becomes the basis for categorizing properties into intensive and extensive. So intensive properties are independent of mass. Examples are temperature, pressure and density. And extensive properties are which depends on size or extent of the system. Mass, volume, total momentum, these are the extensive properties. Okay. Now there are other properties which are called specific properties, which are extensive properties per unit mass, such as specific volume, which is basically volume divided by mass, and specific volume becomes the intensive property. So, typically the specific properties are intensive properties such as specific volume.
Now, in a typical matter, well, the matter of we know this contains of many different atoms, but for us we don't see these molecules or the atoms around. For us it looks like a homogeneous, and this is what we are going to use as an approximation. We are going to use the system as continuum, and this is the idealization. Well, it's not so wrong, or it's not so bad approximation, because if you look at the distance between these two atoms here, in this case this will be of the order of 10 to the power minus 9 meters. Okay, and for example, this is oxygen in certain volume at 1 atmosphere at 20 degrees Celsius, and there are these many molecules in the system. So if you look at this distance and divide by this distance, the order of L by L is going to be extremely small, and in such case this matter will look like continuous, and this is what the approximation we are going to use. So despite the large gaps between molecules, a substance can be treated as a continuum because of very large number of molecules even in extremely small volume. Now this allows us to consider that the properties are also continuous. So it allows us that the property vary continually in space with no jump discontinuity. And considering the system which we are going to look at, because of the size of the atoms which are extremely small, this will be the practical case for all our problems. Okay, so we are not going to take sand particles or grain or asteroid which are extremely large or large in size. So in this course we will be limiting our consideration to substances that can be modeled as a continuum. We will consider this kind of definition. So definition of density is very well known, mass by volume. Specific volume is going to be volume by mass, or 1 by inverse of density. Now you have the specific gravity also, which is the ratio of the density of the substance with the density of the water. Now this density of the water will be considering at 4 degrees Celsius, where the density of the water is maximum. Now you can look at the specific gravity for various different substances. Some are greater than 1, some are less than 1. Those having specific gravity less than 1 will float on top of the water layer. Okay. Now density of the liquid are typically constant, and we will be considering to be constant, so that's why they are part of called incompressible substances, though there are slight change if you increase the pressure substantially, but otherwise we will be considering a constant density in this particular course. Further defined few things. What is the definition of state in thermodynamics? So let us consider a system which finally stops changing at all, so it undergoes a change and then reaches a point where no changes in the properties are seen. In such case one can measure the properties, all kind of properties. So a specific state means a specific values of the properties. So if you fix the values of the property, you achieve a particular state, and this is an example. You have a state 1 with a mass 2 kg, 20 degrees Celsius and 1.5 meter cube. You change the volume to 2.5, you change the state. You are changing just one property of the state, and you are changing the state of the system. So that's how we're going to define a state, having a fixed set of properties. The other aspect of thermodynamics we are going to deal with is equilibrium. There are various different kind of equilibrium. So let's look at what is definition of equilibrium. So equilibrium is a state of balance. There is no driving force or unbalanced potential within the system. So let's take a case where you have variable temperatures within the system, okay, and after isolating this closed system, it reaches a continuous or constant value of the temperature throughout the system. So a closed system reaching thermal equilibrium, this is an example for that. Now if you take a system and isolate it at equilibrium, there will be no further change. So after this particular system, if you isolate it, there is going to be no change. So even if it is a closed system, let's say if I don't isolate it, I let it equilibrate to a specific temperature, and then you isolate this isolate, then there will be no further change in the system, because there will be no interaction with the surrounding. Okay. So that's how we're going to have defined equilibrium. There are many form of equilibrium. A system is said to be at equilibrium when all kind of equilibrium conditions are met. The equilibrium conditions are thermal equilibrium, mechanical equilibrium, chemical equilibrium. So let's look at one step by step. Thermal equilibrium will be where there is no temperature gradient. That means there is no driving force for heat to flow. Mechanical equilibrium is when there is no change in the pressure with time. So there is no driving force for a fluid to flow. So pressure can change within the system with elevation, but in such case the forces will be balanced. Then you have this chemical equilibrium. So if there is no changes in the chemical composition of a system, then the system is at chemical equilibrium. So for example, you can consider like sugar dissolved in water, and there is no changes in the chemical composition throughout your system, and it will be said at chemical equilibrium. Now there is something called phase equilibrium. Now this is relevant when you have more than one phases. So phases such as liquid, gas, solid. So if you have, for example, two liquids, let's say oil and water, after you shake and you let it stay for a while, the oil separates and water separates, and there is no change in the composition of the oil and as well as in the composition of water after a while, and they will be considered to be at equilibrium, because they will meet the thermal equilibrium, they will meet the phase mechanical equilibrium, as well as they are at phase, two different phases. So hence a phase equilibrium is a system which involves two phases, and when the mass of each phase reaches an equilibrium level and stays there. So this is an example of phase equilibrium. Alright, so now we know that the state has a series of the properties or set of properties, and if you change one of the property, the state will change. But it's not necessary that you have to define all the property to fix a state. There is a minimum number of properties which you must define, and the rest of the property gets fixed upon once you define this minimum number, and that is how that is what the state postulate tells us. So state postulate is the state of a simple compressible system which is completely specified by two independent intensive properties. Okay. Now what is a simple compressible system? Which is a system which involves no electrical, magnetic, gravitational and surface tension kind of component. If you have those, then you have to include another variable in order to define the state. Now this is an example of a specific state where just two variable has been defined, temperature and specific volume. Okay. Now you can make use of temperature and pressure also, but this is relevant only for single phase. For single phase, temperature and pressure are independent, but for two phases, for example, where water liquid is converted to vapor, then the temperature and pressure gets related. So this is kind of an example where you know that at sea level, when the pressure is 1 atmosphere, water boils at 100 degrees Celsius, right? And when you go to the mountain, the pressure is less than atmospheric pressure, and the boiling temperature also gets reduced. And in such cases, when there is a phase change, temperature is a function of pressure. The temperature of the boiling temperature is a function of pressure. Any state you can change along during the process. So we'll be defining the process here, that any change from one equilibrium state to another. So this is an equilibrium state, and this is an equilibrium state, and this is a process path. Okay. So a process path is the series of states through which the system passes through. So essentially it means that each of them along this green line is a state, and this is a specific state. This is a specific state of our interest. Now there are processes which are very fast, there are processes which are very, very slow. A slow process where the intermediate point along the path are at equilibrium or quasi-equilibrium is called quasi-equilibrium process. So this is an example where you are using the slow compression in order to make use of equilibrium thermodynamics. So where what you are doing here